right, let's the fun begin. And you may be surprised how easy the fun will be for this particular problem, which initially looks overwhelming to students in the classroom. At least that's my experience. But hopefully I can decipher the problem for you and show you how quickly this can be done. You have seen this problem before and you have already calculated the support reactions. Let me remind you that it's a symmetric system and therefore we have symmetric support reactions as well. And the support reactions that we calculated were really 2,000 pounds on each side. And hopefully you can verify this, and hopefully you don't even have to go back through your lecture script to really understand this, because we have 2,000 pounds acting on one side downwards and then 2,000 on the other side. And to put that in balance, I have to use 2,000 pounds at RAY and RBY. So now our goal is to draw the internal force diagram for the entire system and include all significant values. So that means I have to understand how the system behaves all the way through. Now, you usually would calculate your support reactions first. You would do that on this page, but we already done that in a previous lecture, so I don't want to waste your time with that. And then you need to understand how to use the information from the load case to draw your diagrams. And it's very unlikely that a beginner would immediately put all the pieces together when they have to apply it for this. So I recommend that you would start making a cut at 1 foot, at 2 foot, 3 foot, 4 foot, 5 foot, 6 foot, and so on and so forth, and just do as many cuts as possible so that you can understand what is happening in the system. Now I will actually limit myself and make cuts only at specific points that are at 4 feet and at 8 feet. So where I want to cut the system is to the left of the support. Maybe I also would cut to the right of the support and then at the center. So let's move on to the next page and do those cuts. But before I do that, I say it again. If I was new to this and I would still go through the educational experience, probably what I would do is I would cut here, I would cut here, I would cut here, and so on and so forth, until I have a solid understanding of what's really happening. But I move on now and do the cut at these 3 locations. All right, so here's the space for my cuts. So I do as many cuts as necessary. I start with my free body diagram for cut X equals to 4, and we do that to the left. So really what I have is the overhang only, and I have an evenly distributed force on top of there that is acting with, I believe, 200 pounds per foot. So 200 pounds per foot here. And I cut the system right here, which means I have to bring in my internal forces. So I have my moment, I have my shear force and my normal force. And yeah, it looks strange because it's just hanging in air and you may think, there's no support here, so why can I cut here? But keep in mind that every part of the structure is in equilibrium. So I can now calculate M at 4 to the left. I can calculate V at 4 to the left and N, but I'm going to spare N from now on because it's really equal to 0. So to calculate my V, you can already see what's happening, right? Because my distance here is really equal to 4 feet. I can write out one last time the equation for you. So the sum of the forces in the y direction is equal to 0, upwards positive, and 0 is equal to minus positive defined V for left minus 200 pounds per foot multiplied by 4 feet. All right, and now I find that my shear force at 4 to the left is really equal to minus 800, right? 800 pounds in this case. And that is important to understand that it's minus, because that means we have to draw it underneath the beam. Now for my moment, I have the sum of the moments about 0.4 to the left is equal to 0, counterclockwise positive, and 0 is equal to positive defined rotational sense plus m4 to the left, and also plus 200 pounds per foot multiplied by 4 feet. And now be careful, because if you look at the units, you have feet and feet crossed out, and that's pound. But we are obviously looking for a moment, and so it needs to be pound foot. So I need to multiply this once again with my lever arm, and that is 4/2 feet in this case. So that is the lever arm from here, where the centroid of this cut system is, to here. And therefore, I can now calculate the moment, and m at 4 to the left is really equal to negative 1,600 pound foot. So again, it's important that it's negative. And I want to stress this, that we actually calculated by rotating about this point, which is the first time that we actually calculated internal forces for evenly distributed load cases. And so I did this no different than assuming that this was a cantilever support, right? You learned this before. And so now I have a cantilever support here, which is actually an internal force. And I used the force per distance times the distance multiplied by the lever arm, which of course results from an evenly distributed force that is having a lever arm that is half its distance. And that's where this 4/2 is coming from. But now I'm done with that, and I can move on to my free body diagram for the next portion. So now I can do my free body diagram for cut x is equal to 4 on the right. And that does not look very different, but it looks slightly different, because now I have to include my support reaction as well. But first I include the evenly distributed force, which that's still 200, right? But I also have to include the 2,000 pounds now. So 2,000 right here. And that's pounds. And this is pound per foot. And please understand that we cut right here. And therefore I need to bring in my load, my internal loads, my moment, my shear, and my normal force. But that is equal to 0. We don't care about that. Now I can calculate the sum of the forces in the y direction being equal to 0, positive upwards, and 0 is really equal to v4 to the right. And let's include this one here as well. So now minus positive defined v4 to the right minus 200 pounds per foot multiplied by 4 feet and plus 2,000 pounds. And that concludes the shear force for V at 4 to the right. And yes, you can already see that it will jump, right? Because now I have to add the 2,000 to it. So I'm going from negative 800 to plus 1,200 pounds. And that now gives me the shear force. You can convince yourself that the moment would not change. So the moment here just increased a little bit the lever arm, and the 2000 has no additional lever arm to this internal force. Therefore, I can state that M4 to the right is really equal to M4 at the left, and I don't even calculate that. So that's also equal to minus 1,600 pound foot. And it's one thing to calculate the values. You actually need to understand the shape of the diagram, and that's again why I suggest that you make another cut maybe here and here, so that you understand how you start from here to get to this point. I, of course, can take shortcuts because I've solved so many problems before. I've gone through the educational experience that you are currently going through. And that is why I am able to explain that to you and why I can do this fast. You should not fall into this trap of just doing this if you are puzzled, right? If you already have the answer, by all means, you don't need to do more work than necessary. But if you could not draw the diagram based on these numbers right now, I would encourage you to find the internal forces maybe at 2 feet and then maybe at 0 feet so that you can actually build up the diagram yourself. Let me, just for your educational benefit, go ahead and calculate the moment at the center and the shear force at the center. So let me do a cut or the free body diagram for x is equal to 8 feet, right? So that's where we will have the center cut, if you will. And to do that, I have to now include the entire beam with all its load cases on it. So we had 200 here and then the 300 right there. And of course we cannot forget the support reaction. And I probably should also in this sketch include the dimensions so that we're not confused here because it's not really to scale. So let me go ahead and say that this is 4 feet and this is 4 feet. And this was 200 pounds per foot and this is 300 pounds per foot. And of course we have 2000 pounds right here as a support reaction. I cut the system right in the middle, so that means I bring in my internal forces and I know that n is equal to 0. But now I can go ahead and calculate my shear force first. So let's go ahead and do that. Let's say that the sum of the forces in the y direction is equal to 0, upwards positive, and 0 is equal to v at 8, I guess, right? So this is v at 8 and then this is m at 8. So plus v at 8, but it's going in the negative direction, so therefore negative, minus 200 pounds per foot multiplied by 4 feet minus 300 pounds per foot, and that also happens to be multiplied by 4 feet, but that is the 4 feet on the right side, so don't confuse those. And then I also need to include the 2000, so plus 2000 pounds. And surprise, surprise, v at 8 is actually equal to plus minus 0. Right? This is important to understand, and it comes actually from the fact that the system is symmetric. I will explain that when we actually look at the final diagram. Hopefully this doesn't surprise you too much that it's actually equal to 0. Let's calculate the moment. So the sum of the moments about point 8 is equal to 0, counterclockwise positive. 0 is equal to plus m8, which is also rotating in the positive direction, plus 200 pounds per foot multiplied by 4 feet. And that now needs a lever arm. And keep in mind that we are actually having the centroid of that force right here. So therefore, I'm looking at a lever arm of 4 over 2 plus 4 in this case, feet. So that is the lever arm from here to here because I'm rotating about that point. That means that I now have to include the 300, so plus 300 pounds per foot multiplied by 4 feet multiplied by 4 over 2 feet. Because now I cut right through the 300 pounds per foot force, and that has a centroid or a concentrated force or a force resultant right in the middle, and therefore I'm looking at 2 feet distance here. But I cannot forget, of course, my 2000, which now rotates in the opposite direction, so minus 2000 pounds multiplied by 4 feet, because again it rotates about my green cut there. And if I do those calculations correctly, I will find actually that my moment at 8 is really equal to plus 800 pound foot. And of course the plus is important, as you will see on the following page. Let me underline my result here and let's take a look at the final calculations, which, I'll be honest with you, if I had enough practice in this, I actually would not even calculate anything. I would have just go ahead and draw the diagrams. But you see how I arrived at these significant values and how I used equilibrium for the force and the moment to determine the internal forces at these particular cuts. If you can now go ahead and use these few data points to really draw the internal force diagrams properly, more power to you. That's exactly the point you want to reach in this class. But it is my experience in the classroom that these few values do not lead to successful completion of the diagrams. Of course, I will show you now on the next page how you actually draw these diagrams. But please don't be fooled. It's always something different if you have knowledge explained to you than if you create your own knowledge. Why am I saying that? Because you cannot shortcut knowledge, right? You have to go through the learning experience, and there's really nothing wrong with drawing these cuts and solving these values for additional cuts if you are not there yet. That is something you actually need to do. In fact, that's something I had to do over and over and over again to be able to explain this to you. So this doesn't come from nowhere. This has nothing to do with somebody being smarter or anything. It's just people are more trained in certain concepts. And so please do yourself the favor and really train this concept and practice, practice, practice. And if you cannot connect the dots yet, it's very simple. You just make another cut at 2 feet, at 6 feet, at 8 feet, at 10 feet, and so on until you understand it. Again, there's no shortcut to your own knowledge. And just because somebody explains something to you and you understand it doesn't mean you can apply it. But in this class and in engineering, you will have to apply this all the time. So if you already have enough data to do that, that's good, you reach the goal. But if not, please expose yourself to more of these cuts, because in the future I will now, from now on, start just drawing these diagrams and explain where it comes from. But it shows up as a surprise to some students sometimes, and it's not a surprise because I have done these things that you see here on this page so many times that I can do many of those things in my head by now, and hopefully you will reach that point too. Maybe you're already there. I'm pretty sure you're much smarter than I am, but I encourage you to practice that until you really understand the concept. Otherwise, there's no point in moving on. But I will now explain to you how these diagrams are drawn, and that of course gives you an additional help. But don't confuse following my knowledge with you understanding the concept and applying the concept. All right, enough talk. It's time to draw the diagrams, and to do that I bring down, as always, my indicators here of where something interesting happens. And actually something interesting happened also at the center line, so I bring that down as well. And then I can start drawing my internal force diagrams. Let's get started with the normal force diagram. So that actually happens to be 0 in pounds in this case, so I don't need to waste a lot of time on that. And then let's go ahead and actually indicate that all of this is 0. And yes, I have to do that for every individual region. But now I will draw the shear force diagram. So we have V here in pound. And the values that we calculated were really minus something. What did we calculate? Minus 800, if I'm not mistaken. So minus 800. And then also plus 1,200. So what did I calculate? Oh, I also calculated 0 here. So this was 0. So minus 800, let's pretend that's right here, and then the plus 1200 is right there. Now the question is, how do I connect the dots? And again, if you don't know that, please calculate more values along the beam. But I know that I have to have 0 at the beginning, so this has to be 0. And I know that I have an evenly distributed force. And it also has to go down, 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 down with 200 per foot. So it actually becomes fairly easy once you internalize that. And that is that I have a linear function here that goes down to minus 800. Then I have a jump of 2000 up. And then I go down to the 0. And now you may ask yourself, how does the other side look like? And I let you think about this for a second while I complete this. And maybe you can go ahead and do that. I often see a common mistake in the classroom now that the students actually think, okay, it's a symmetric system, therefore it goes up here and then goes down and then like this. But one thing we need to talk about is that if the system is symmetric, the shear force is actually anti-symmetric. And you can make clear sense of that because at this point I need to continue going down with a slope of 300 pounds per foot, right? Because you went from here to here with 300 per foot down and this doesn't change here, so I need to continue. And then I'm jumping up by 2000 and then I go down with 200 per foot here as well. So the way that looks like then, it would be a continuation of that first center slope here. So that would look like that. And therefore I would end up with a value of minus 1200 here. And then I jump up by 2000, which means that here I'm looking at plus 800. And then I have to have a parallel line to the first slope, which would look something like this. And what did I mean by the parallel line to the first slope? I will indicate that for you in just a second. And I mean that this line here is actually parallel to that line. And likewise, this line is really parallel to that line, but that is clear from the picture. And now we have all the significant values included, right? We have the 800, 1200, 1200, and 800. And I can now start drawing my moment diagram, my bending moment, which happens to be in pound-foot. And what do I know? I know a few values. I know that I have a negative 1600. So here I had negative 1600. And at the center, I had a plus 800. That makes it a little bit complicated maybe, but I think we can decipher it. Do I need to calculate something else? Probably not, because I know that the moment must be 0 here. And if you do not believe that, you can convince yourself by just making a cut at that location. But I tell you it's 0 right now, and let's just say that we agree on that. And now I also know that I have a slope that increases further down, down, down. And remember, we have a distributed force here which produces the slope. Therefore, here we'll look actually at a cubic function. But it's a negative slope this time, right? So let's actually give us some more space here. And let's say that I have minus 1600 right there. And so I have a little bit of slope, a little bit more slope, and more slope, and more slope. And so this here actually is supposed to be parabolic. And now how do I get to the 800, which let's pretend that's right here. Now I need to compare that to this slope here. So I have a 1200 value here, and then in the middle I have 600, and then here I have 0. So that means that I have to draw a tangent here that is 0. Here I have a very steep tangent, and then I have some tangent in the middle. So that means I definitely end up with a belly up, as my students call it in the classroom. And now I have the left side completed. This, of course, here is all negative, which makes perfect sense if you think about it. Why is negative making sense? Because this beam here is clearly frowning, right? It wants to bend down this way. So that means you have tension on the top. and compression on the bottom, which is the opposite to what we usually have. So think of this part as a cantilever, and therefore we have negative bending here. And then there comes the inflection point. So there's actually bending that goes on here, and then here there's some inflection in the bended shape, and therefore we end up in the positive region up here. Now the question is, how do we continue our graph? I want you to think about this. How do you continue at this location and at this location? And probably the easiest to start with is right here, because you know it must be 0 there. And then what do you do? I think the easiest thing is to follow this slope. I'm 0 here, and then I'm getting negative in my slope, right? 0, negative, negative. And then here I have a positive slope, and it goes from a lot positive to less positive. So therefore, it's actually a mirror image of what I already have here. So I just need to image that over or mirror that over and draw my belly shape here to negative 1600. And then I copy the other side, which was a little bit flatter. And that now gives me my entire diagram, which is negative here on the bottom as well, because I have the very same physical behavior on the right side. Everything here is bending downwards. So here the beam is frowning, and it's actually frowning all the way up to here. So this part is frowning or bending downwards. This part is bending negatively or frowning, or the top is in tension. Whereas from here to here, the bottom is in tension and the top is in compression. And so this is really our first problem for which we saw a linear, or sorry, I should say constant load case. So we ended up with a linear shear everywhere in this case. And then we had a parabolic moment. And by the way, I have to indicate which region is parabolic or cubic or linear. I have to write this next to my diagram when I take a test, because I cannot tell by hand the difference between a parabolic and a cubic function. So I always would include that as follows. Like, let's pretend that we have different regions here. Of course, here it's all the same, so I don't have to really do that, but I would state it like this, that from here to here it is parabolic. And that needs to be clarified, otherwise we cannot provide all the points. But also I included all my significant values here in my diagrams. I included the identifier and the units, and therefore I consider this problem completed. It can go fairly fast once you know what you're doing. Don't be surprised, but again, don't fool yourself. Don't just draw these diagrams, because that will not work out well for you in a quiz or in an exam. I've seen that go wrong many times when students just try to draw. And we can talk about those more in the future, what kind of funky shapes I sometimes see. But for now, we completed this problem, and it's time for us to move on from evenly distributed forces to non-evenly distributed forces. But we will do that on the following page in a brand new example. All right, so here we have our next problem, for which we once again are asked to draw the internal force diagrams. So we have to do that and include all the significant values. This now is a system that has a pin on the left side, a roller in the middle, and then an overhang or a cantilever, which is loaded with an evenly distributed force of 4 kilonewton per meter. And then here we have a sloped distributed force, or a linear distributed force, which is non-evenly distributed and is acting from x equals to 0 to x equals to 3 meters. And I don't want to waste your time with support reactions or with even calculating internal forces right now. That's not our goal here anymore. You can practice and practice and practice that. But the one thing I want to point out here is the physics of the system. So if you take a look at that, you can see that we have 4 kilonewton per meter over 3 meters. And here we have exactly half of that acting. So therefore, we immediately know that the support reaction on the left side actually has to pull down, because we have an imbalance that rotates about this point. Think about what would happen if you would remove the support. and then have it balanced over this point. Clearly, because you have more load sitting on the right side, it would rotate clockwise about point B. And so I have to balance that. And if you run the numbers, what you would find is that your support reaction at A, again, is going down, but that actually happens to be 4 kilonewton in this case. And therefore, you have to push up with a little bit more than what's actually sitting on top of the structure. And you have to add the 3 times 4 times 1/2 here, half because we have the triangular distributed force, and then 4 times 3. And what you will find is that actually turns out to be 22 kilonewton. So I have 22 kilonewton. But you can calculate and verify that by the means of the procedures that we showed you in other lectures. So I will now move on to draw the internal force diagrams. I will not even have to do a lot of calculations. I actually do that as I draw the diagram, because the only internal forces that I really have to calculate are at this location, because everything is already clear to me, but you will see that on the next page. So here we have the system with the empty diagrams given to us, and the first thing that I do is I bring down all my important locations, which I now have them all, and I can of course immediately start drawing my normal force diagram, which in this case I'm actually going to put here on the bottom. So I say that this here is the normal force, which happens to be in kilonewton, and that is all equal to 0. And I should of course draw a 0 line through that. So let's do that. And the reason I put it on the bottom in this case is so that now I can better see all my diagrams at once. All right, let's go ahead and start with the shear force diagram here on the top, which is also in kilonewton, and I like to actually develop them at the same time, so I also start immediately with my moment diagram in kilonewton meters. Now, what do I know? I know that all my diagrams always have to start at 0 essentially and end at 0, so I can already say that they are starting here, and the same is true for the moment, and it has to end up at 0 there as well. Now, what else do I know? I know that I have a distributed force that is non-evenly distributed and an evenly distributed force. So that means I know what's going to happen here and I know what's going to happen here. Let's actually indicate that, and let's say that I end up with a parabolic function here, and I will have a linear function in this region. Now remember that my support reactions were given with 4 downwards, 4 kilonewton, and with 22 upwards. So now I'm pretty much done actually. I mean, not done, I have to draw it, but like I have all the information I really need because I can follow my arrows, right? So I have to go down with 4, start from 0. So let's do that. So I'm going to go down here to -4. And now what happens? I have to go parabolically down to some location. Why do I know that I have to go down? Because I follow my arrow. And why is it parabolic? Because my first arrow is short, the next one is a little bit longer, the next one is even longer, and then very long. So from this point here, I go down, 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 further, further, further down. And so you see it must be parabolic because with every step I go to the right, I go more down. I go to the right and I go even more down. And I go to the right and I go a lot down. So therefore it has to be parabolic. Now where that value is, I don't know yet for sure. I will calculate that in a second. But I know that at this point I will actually have a jump. So let's pretend that I have this here. And then I must have a jump that follows my arrow of 22 up. So now the question is, am I less than 22 here? So do I go through 0 or not? And there's 2 ways I can think about this. One way is I can relate it to the moment diagram, because I know that the bending moment must be maximum over this location here because I'm pulling down. I make the beam frown here. And so therefore it has to pull down. But another way to think about this is I can also invert my logic. So usually we start on the left side and then we follow the arrows, right? But here I have to end up at 0. And so that means I have to follow this arrow down, 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 down to end up at 0 here. And what's easier than calculating from 0? Like, we have to go from 0 to here with 4 times 3. So all I have to do is really use a linear function there, as I indicated already, and I have to go down from the left to the right so that I can end up with this equation here, or this function. And this value here is really plus 4 times 3, or in other words, plus 12. And so plus 12 then has to be the endpoint of my jump from here, and the jump has to be 22, and therefore I can already connect those dots, and I can say that my value down here is actually minus 10 now, right? So I have minus 10 there, and I have to go parabolically to that point. So let's pretend that I can draw this properly so that somehow this is my parabolic function. And granted, I should now fix this right here. So my x was not right there, but I'm not drawing to scale anyways, so therefore that's okay. I now have a jump from minus 10 all the way up to positive 12, because together this is 22, and I have my entire area here on the left side in the negative shear force, and on the right side I have the positive shear force. And I know the functions being linear because this is a constant, and parabolic because this is a linear function. So I now have actually completed my shear force diagram. It can be that simple if you know what you're doing and if you have experience with these problems and if you practice a lot. Now, talking about practice, let's look at the next diagram, which is the moment diagram. We have to now understand if we're talking about a positive or a negative here. So along this line, we obviously must have a maximum. So I can now debate with myself, do I have a maximum value here on the top, or do I have a minimum value here? And how would I figure that out? I know that I have to start at 0, and I know that I have to end at 0. And I think the easiest way to think about it is to release this part of the beam, the right side, so that you actually draw the free body diagram. And I'm just going to introduce my cut here. So I just do it here for now, just because we want to be fast in this example and I don't have to steal more of your time. So I now look at the right cut here, at this portion, and therefore I have to put everything within that cut cloud into equilibrium with that moment. And you can see that the moment is turning clockwise and everything in this cut cloud is also turning clockwise. Therefore, this cannot be in balance unless I flip the arrow around. So what does that mean if I flip the arrow around? It means that it's negative. And therefore, I know for sure that this is the right minimum and this maximum does not exist. So let's actually erase that maximum right there. So let's go ahead and get rid of that. And now I can use my knowledge from the previous pages, and I can state that because I have a linear function here for the shear force, my moment must be, of course, parabolic, right? Parabolic. And likewise, here I have a parabolic function, and if I integrate that, I end up with a cubic function. So let's write that. And of course, it's difficult to differentiate this drawn by hand, like how much one thing is a cubic function and one thing is a parabolic function. But of course, you get the idea. So we can now draw this area here as being negative. And the last thing that I need to do is really calculate this point here on the bottom, the M min. And I already know that that is a negative value because I, of course, have indicated that and I explained to you already why it's negative. But how negative is it? It's already included on this page because I already have the cut here and I need to find this internal force. So how much is that? So M min is really equal to 4 kilonewton per meter multiplied by 3 meters multiplied by 3 over 2 meters. And this, of course, is negative, as we indicated already, and therefore I know now that my m min is minus 18 kilonewton meters. And that is already the entire problem, and I included all my significant values. So let's take a look at this problem and summarize real quick. Of course, I don't need to talk much about the normal force diagram. That is 0 because we have no horizontal force. But the shear force diagram here was created starting from 0 and ending at 0 here. We knew that we have a linear increasing load case, therefore we needed a parabolic function underneath that for the shear force diagram. And for the constant or evenly distributed force, we needed a linear function. Now, how did we get there? I knew that I end up at 0 here, and I knew the slope of this linear function. So I used the reverse method, going from 0 to 12 by a slope of 4. And then I had a jump down, which was equal to the 22. And I also knew that I had to go down here by 4 because I have a support reaction that's pushing down. And through the parabolic function and this jump here, I knew how to connect those points, and I knew that I went through 0 here. Which therefore meant that for the moment diagram, I have a minimum here and not a maximum. I have a minimum. I knew that it must be cubic because if I integrate a parabolic function, I end up with a cubic function. And on the other side, I have a parabolic moment function because I integrated a linear function. The minimum moment that I calculated here with minus 18 was really derived from a cut in which I separated the right side. I could have, of course, done the left side as well. It doesn't really matter. And some students are sometimes hung up about like, why can you cut the right side to the right of the support? How do you know it's the same as on the left side? You would definitely know that from everything we discussed in this class before. So don't get confused about that. I used the cut cloud here, and that is definitely a proper method of doing that. But I want to put your attention to the shear force diagram here and to the fact that we integrated from here to here. And what is integration? Integration is really the area under the curve, right? So if I want to find the area under the curve here, what would I find? I would really find 4 times 3, which is equal to 12. So this value here is 12. Please do not get fooled by this minus 10. That's the value down here. So 12 is the height of the triangle, and then the base is 3, right? And how do you calculate a triangle area? You do that by using the height. And then here you have the 3, which is the base. And then you have the 1/2, right? So really this is base, which is the 3, times height, which is the 12, divided by 2 because you're looking at a rectangle that is cut in half exactly along the diagonal. And so, yeah, we do not have negative areas, of course, right? We have a negative 18 here, but the area content under this triangle is really 18, and so it reflects actually the content here. You could also find the area under this curve, and that would also give you 18. Right, so you have a rectangle in here and then a parabolic function on top of that. You could integrate that and you would find that this value here is minus 18. Or you would find 18 and then you would understand that it's negative because we're dealing with negative bending. But that explains, I believe, how I arrived at these diagrams and some shortcuts that you can take to really draw these graphs effectively. Don't get me wrong, there are many different shortcuts that you can only learn through practice, but lucky for that, we have actually a lot of homework problems. So I think you can apply this knowledge in your upcoming homework. But before we do that, let's take a look at the summary page for this lecture, and let's then conclude this lesson.